Alexander-Universität Erlangen-Nuremberg. I hope correct.
It's always a challenge.
And he's the chair of applied mathematics laboratory, especially modeling and numerics. And as you may know, he has been actively working many fields, especially by my understanding, image processing and imaging, and he has established the celebrated works. And today he will give a talk entitled by, just a moment, maybe the already shown kinetic models and parentheses, social parentheses, networks. Could you start?
Yeah. Thanks a lot for the kind invitation and the opportunity to give a talk here. I was asking Enrique what he finds more appropriate, and so we chose a topic that is not on inverse problems, but on kinetic models, and something I think is quite timely. So in the last years, there is a strongly increasing interest to get models of microscopic phenomena that emerge from social interactions. The social interactions have been there, of course, for centuries, but somehow in the last decade, with some kind of experimental test beds like Facebook, Instagram, or Twitter, there is now much more observations made, and also kind of the type of interaction has changed, and so we see more clearly what is coming out of this. So examples are, of course, opinion formation, where you observe phenomena like either consensus or polarization, and which I will come back to. Then something that is also somewhat interesting now is how you establish or change social norms, or things that are accepted in societies. You see this also in all kinds, like if you look into some Western societies where you have more rights for minorities, or if you look into other countries where they decrease rights for minorities and still establish this kind of as a social norm that is well accepted. Or some other examples are like the exchange of knowledge or rumors on networks, or also language interactions, dialect changes that are modeled in similar ways. Okay, naturally, these interactions happen on networks, so typically social networks, but you can also think about other abstract processes on networks or graphs. And the point is that also these networks are changing in time, and this is something that has not been much considered particularly in the mathematical literature, but also in general, it's not very standard. So what is kind of the key phrase is there is a coevolution of some state, which is a function on the nodes of the graph, like your opinion, your social norm, whatever, and of the graph itself. So either you think about a weighted graph, then it's the weights, or if it's just a binary, then it's just the edges that are switched on and off in time. And in the social, or I would say there is something what's called computational social sciences. Now there are several papers, basically all in the last 3-4 years, or including this book that discusses these issues a lot, where they discuss about agent-based models for this kind of thing. So they kind of create arbitrary agent-based models, do some simulations, and try to infer something out of this, which is always kind of a tricky thing in terms of how do you choose parameters, what can you really learn about specific simulations. So of course, as a mathematician, you would like to come up, first of all, with more generic models, and then give more generic statements. What is kind of the large time behaviors? What are the patterns that naturally emerge under certain conditions from such systems? And let me remind you about the talk by Christina Pinotti last week. She was considering the Hexelmann-Krausen model or similar models for opinion formation. In her case, also with delay, which I don't want to touch in my talk. But the important thing, remember, also in her case, kind of there was a changing network hidden in this communication rate, Aij. So there was the tendency to get towards consensus between different opinions of different nodes, but there was this, in this case, instantaneously built kind of network between node J and node I, which depend on the differences in their states. Okay, and so you could think about this Aij as actually the weight on a weighted graph, which is changing in time. So it's exactly kind of this setting that appears. But yeah, I'm interested in a bit more general situation than this, what is described by the Hexelman-Krause model. And typically also in Hexelman-Krause, it's not presented this way. So the way it's presented is all about kind of the state variables. So for example, your opinion between 0, 1 or -1 and 1. So here are two simulations, and one showing consensus, one showing polarization. So the typical viewpoint of this is you look at the state variable as a function of time, or maybe at multiple state variables, and you check what is going on. Okay, this is also somehow the traditional way to record opinions. So you ask, okay, for example, in the US, how are you considering yourselves towards being liberal or being conservative? And then you see, okay, these things are kind of polarizing. So here you have a mean value, and then or median, and then these go apart in time. However, this only tells you a part of the story, because from this point of view, you are not seeing how the network structure will be in time. So what maybe you're more interesting, and this is a simulation we did based on a model from this paper here, which has continuous state and discrete edges. So either they're there and then the weight is 1, or they're 0. So it has a very similar evolution of states like in the Hexelman-Krause model. So you see that you go to some kind of polarization, but what is maybe more interesting also is the question, what happens with the network? So initially, or at very early time, the network is quite strongly connected, but in the large time limit, you basically delete all the links or most of the links between the agents with different state, or in this case with different opinions. So this is what you call an echo chamber now on networks or on social networks. Okay, and this is something that of course is an interesting question. How is polarization done? Is it automatically leading to social networks, and it's also to polarization in the network? And the question is then also, what is the stability of such a pattern? Of course, if they are fully separated, then you have kind of sub-networks where you have consensus, and then this will be very stable. If not, you have a chance to at least do something to get out of these strongly polarized states. Okay, and most of my talk, to be mathematically precise, I will use a paradigmatic model, which is kind of corresponding to some Vlasov type dynamics with an appropriate scaling. Particularly in the weights is maybe not the most natural model to consider. So typically would like to have more stochasticity, but once you have understood the mathematical issues for this model, you can treat also all the other models in a similar way. Okay, so what we have is simply like in basically all the opinion models, we have an evolution of the state variable, could also be multidimensional, as a function depending, in this case only with pair interaction, on the state of the other, but also depending on the relative weight. So for example, you could say this function is the weight times some kernel applied to the relative state. Okay, so then this is what you find in Hexelman-Krause essentially. And then you have an evolution of the weight, which maybe depends on the weight itself, but also on the relative states between the two agents. So here you could introduce some kind of homophily so that you maybe have a tendency to rather connect to people who have similar opinions, or what, for example, Facebook or others do is that they actively propose you to connect to such people. So this is this trend that you could introduce here. So for example, it could be a function of, again, the relative state, and there could be some kind of random change or random, disconnection, in this case, if kappa is positive, that you have. You see already, if you rescale this in the right way, so if you have a potential like this, depending on the relative states, and you have some relaxation time, there's an appropriate scaling here, which goes to 0. So kind of the dynamics in the weights is a bit different. In this case, it would be faster than in the states. You would go to a stationary solution of this, and then you can compute the weight as a function of the relative difference in the weights, and then you go back to this bounded confidence model. So compute the weight from here, and then you put it here, so it looks like the standard models. Okay, so there is the connection that you see here. Okay, there are some other special cases that you can incorporate. So if these functions u and v are independent of the second state, so only depend kind of on yourself. I think that's wrong. It's only v should be independent of sj, otherwise it would be too boring. And then you can get special solution where the weights are only depending on the first agent. So this is kind of only an interaction strength, not a relative scaling. And this is the case that has been considered by Poradier-Dutet and Piccoli in several papers in the last years. It's mathematically a bit easier to treat than what I discuss here. Or you could also have what I call network structured model, where you kind of have a state variable that depends on two parts. So you might think the x part is kind of a location of the particle, and the y part is kind of the opinion or some other social state. And of course, typically you could think, okay, the location is maybe stationary, so kind of the u component corresponding to x is 0, so you only have a dynamics in y. And if you then have a similar relaxation limit as before, so that you have some kind of tau to infinity, and you can compute then also the weight as a function of these first two states in the right way. Then you go also to these kind of structured models where it's more like towards spatially structured models. So your interaction then in the end effectively only depends on xi and xj, so kind of on the location, and you have some kind of standard interaction. Okay, so there's all kinds of special cases you can go through. Another one, just for more the mathematical analysis, is of course what is the gradient flow case up to some scaling that is due to the mean field scaling here, which basically you can ignore at this point. If you have some energy function of the states and the weights, several of these models, in particular the model from before, if the kernel is a gradient of some potential, then you can write them as a gradient flow in this form. And for the canonical form, a typical energy would be to have this kind of weighted interaction. So the typical interaction models would have a stationary weight here and some kernel here. Okay, if the weights are also introduced, then you may have also some additional terms that only depend on the weights, and then it's here kind of a even more nonlinear term in the energy. Okay, so that's another case that I will come back later, and or at least where you can better understand what are the patterns, because you can look at the minimizers of this energy, which are also not completely trivial to get, but which is easier than for arbitrary dynamics. Okay. As I said, this paradigmatic model is just a special case of a more general model structure that you might have. So you could have, in general, some continuous time Markov processes in state and weight, so some jump interaction and so on. And then you can write it still in a very similar form as before. So the first line is basically what we had before. If you trade the divergence to some generalized operators, so this could be some non-local or discrete difference operator if you have jump processes. And then you could have additional effects like external potentials or some kind of diffusive effects if you have enough randomness, which I don't go into detail at this point, just to tell you there is basically a very similar treatment for all kinds of other processes that people discuss in these agent-based models. Okay, and one example just to give you, because this is frequently considered, is what's called the co-evolving voter model, which is then a completely random model, and a completely discrete model. So you have a binary set of states. So you say, okay, either I am in favor or against something, so to be +1 or -1. And you have basically a non-weighted graph. So you have weights which are 0 and 1. And then what you say is basically you do some random interaction between connected nodes. And if the states are opposite, either one of them changes its states or the edge is removed. And in the latter case, you may create new edges. And you can write this as having kind of 3 rates. You have a rate of changing states, you have a rate of establishing new edges, and a rate of removing edges, and all these will depend on the states of the 2 interacting particles. So will be functions of Si and Sj if I and j interact. Okay, and I will come back to this model in the end if I have enough time, because there we can say a bit more about polarization. What I'm mainly interested is, of course, large networks, and then the natural question is how to go from n to infinity. This is, of course, the classical idea of kinetic theory or statistical physics. And as an Austrian, of course, I have to mention always the work of Ludwig Boltzmann, which was kind of fundamental in this area. And the way to go from microscopic to macroscopic is to first describe a high dimensional probability measure on an n or n times something dimensional space. So you have a probability measure that really describes the probability that first state is equal to this, second state is equal to this, and in my case would also be first weight equal to this, second weight equal to this, and so on. So it's a very high dimensional measure. And what you're interested in is kind of the, typically in kinetic theory is the first marginals, like the one, what you call the one particle density. And the way to go there is to consider really the infinite limit, or first the finite hierarchy of marginals of this probability measure. So if you integrate out n minus k of the n particles and get then a measure for k particles, and this you can pass to the limit for n to infinity, is called typically the BBGKY hierarchy. And then in the end, okay, what Boltzmann did is to say, okay, if I look at these equations for the marginals, there is basically a simple solution, and what he called the German the Stoßzahl-Ansatz, or what you would say is a closure relation, so that basically all these marginals factorize in terms of the first marginal. So you can write kind of the k particle density in terms of the one particle density. This is the typical thing that is called here. So mathematically, let me write it how it would work without the weights, so only the state variables, so u only depending on these two. So this would be the microscopic model. The Liouville equation is just the standard transport equation in n dimensions, and you see directly the microscopic model S dot equals to u is kind of, or it's 1 over n sum of the u's over the other j's. This is just the solution that you get by the method of characteristics for this equation. Okay. And then you go to the marginals. As I said, you integrate out after k all the variables, and you can easily come up with an equation for this by just integrating the Liouville equation with respect to the other variables. So you have the first ones, which are not yet integrated out, and then you have the other n minus k, which you have integrated out, and you can, since all the particles are indistinguishable, you can all of them write all of them in the same way with, say, sk plus 1, since all these integrals are the same. Okay, and then you can pass, of course, n to infinity, and then you see, okay, this first term is kind of going away. These are case terms here divided by n, so this will go to 0, whereas in the second one, okay, this factor will go to 1, so you arrive at an infinite hierarchy, where you always, the equation for the case marginal depends on the k plus first marginal. Okay, and this is due to the special case of two particle interactions. If you have like more particles, like 3 particles, it will depend on the k plus second and so on. But, okay, that's interesting. And then you can check this, what was called the propagation of chaos. So if you have kind of independent particles in the beginning, they stay independent. So there is a special solution, which is a product measure in terms of the first marginal, or what's called the single particle density. And the single particle density then can be computed by the Vlasov type equation. So you just go to the equation for the first marginal, then you would have here the second, and then you introduce it as a product of the first one, and you can compute it. Okay, so this is the basis about all these macroscopic equations. Also, for example, the one considered by Christina last week, you would always get this. Okay, and this is what is called, as I said, it's called propagation of chaos, and there are all kinds of quantitative ways to derive that nowadays. And you can also do it for other equations, of course, not just for Vlas. Now the question is, okay, what do I do in my case when I have the weights? I can write basically the Liouville equation in the same way. Let's see again by the method of characteristics. But then the question is, what are the appropriate marginals I do? Do I do separate marginals with respect to states or weights, or what are the right variables where I get a suitable hierarchy? So it turns out what you have to do, it's a bit complicated to think, but in the end it's quite apparent. What you have to do is you have to take always the first k variables and all their relative weights. Okay, so ck would depend on the first k states and k times k minus 1 weights between them. Okay, so the first C1 is just S1 because there is no other weight. C2 is S1, S2, and the weight between them, W1, 2. And C3 would then have 3 states and already three weights in between them. So you see this is an increasing number. And then I define a marginal by integrating again the microscopic density with respect to all the others. So this is just a shorthand notation for integrating out all the others after k. And then indeed you get to some, again, similar equation for the finite hierarchy. Looks basically the same. You have the 1 over n terms here, you have the other terms here. And since I have no kind of mean field interaction in the weight, it's just nothing changing here. And then you can go with n to infinity and you really get a closed infinite hierarchy. So up to this point, everything is the same as in standard kinetic theory. But at this point, there is a problem now. I cannot get, obviously, a solution in terms of the one particle density, because the one particle density only depends, or the one particle measure to be precise, only depends on one state. It does not depend on any weight. So remember, the C1 here only is equal to S1. There is no weight involved here. So there is no simple solution. So again, just written the equation for the single particle distribution. The first marginal depends on the second marginal, and of course this depends on S2 and W12, so I cannot factorize it. So there is no simple equation that I can come up with here. And so the only meaningful macroscopic models need to be kind of at the level of the two-particle distribution, because this is the first one that really involves a weight between particles. And also from what I want to learn, how are the weights looking, this is the variable I kind of want to look at. Okay, so what I have here is a higher order closure problem. Before I go to this, there's still one case where I can solve things. This is a very special class of solutions, actually, where this weight in terms of state and weight kind of separates into some randomness in the states, but a deterministic part on the weight. So if I have every weight, so this is again very similar to what was there in the Hexelman-Krause model. If the weight is a deterministic function, which can change in time, but a deterministic function of the state, then it really, the randomness is gone. So it really concentrates at this weight. Then I can come up with a special solution. And then I get, for the randomness in S, I have the same issue as before. I get really this propagation of chaos property. And then I can come up with an equation, which is very much like the Vlasov equation, up to this additional weight. And I can also come up with an equation for this weight as a function of the states. And it's basically, I mean, this is just the advection term. So this looks complicated, but it's just due to the Eulerian variables. So it's just basically, in Lagrangian variables, is that the derivative of the weight again is equal to this function v. So like exactly like in the microscopic model. Okay. So what we have is, again, as I said, this coupled system, and this can then really be solved by the method of characteristics. So if you go to these Lagrangian variables, it's exactly like in the Vlasov model. You have an equation for the characteristics in state and the characteristics in weight, which is basically like in the microscopic model. So for this special case, if you have no randomness in the weights, you can come up with a solution, and you can maybe learn something from this here, that you have kind of this kind of characteristic system, which will also work for a more complicated model. So now the question is, how will I come up with a right closure? And what I need to do is to go for the equation for the two-particle distribution and write it. And there is a term depending on the three-particle distribution. So I need to write kind of the three-particle distribution in terms of the two-particle distribution. So what people in statistical physics do when they look at these kind of correlations is they frequently use what is called the Kirchhoff closure. It's the simplest symmetric kind of closure. So you have kind of the Radon-Nikodym derivatives of the two-particle with respect to the one-particle densities, and then multiplied again by the one-particle densities. Okay, so this is kind of a meaningful closure, and then you can write these interaction integrals that will appear with the three-particle distribution like this. So you have kind of the Radon-Nikodym derivative here again, or the conditional distribution up to the first, where I would say, and then you have this two-particle distribution, and you have this additional projected two-particle distribution, which actually is probably not the really interesting thing, because here you have an integral over a function of S1, S3, and the relative weight, and eta2 is really depending, is a projection of actually the other weight between particle 2 and particle 3, which is probably not important for the interaction between particle 1 and particle 3. So what you can also do, and this has been done in the standard case without weight by Chabin and others, is to ignore this term in the interaction integrals. So what you do instead is you write directly not a closure in terms of the three-particle density, but in terms of the interaction integrals that come up in this equation, and ignore this eta term here. And so you have a very simple, effectively have a simpler closure then. And you can also write it, of course, here as an integration with respect to the conditional distribution. Okay. Yeah. And then you could also directly write the whole thing in terms of the conditional distribution and the one particle distribution. which has one advantage, because when you do this, you basically already know how the method of characteristic would look for the one particle distribution. So it's this equation here. And for this equation, you can also have basically only to come up with the characteristic for the W, and this equation has a nice one. So you can write like before, really the characteristic equation for this system, and then yeah, get at least a solution and make sure it's interesting. Okay, there is another interesting property of this closure, is again, when we go back to the gradient flow structure, we can also write, okay, if we had these potential relations in the microscopic setting, we can also write a macroscopic energy functional. So the discrete one was the sum of f of S1, S2, and W, or Si, Sj, and W. The macroscopic one is then, of course, just the integral. And the interesting thing is, if you now look at what happens with the gradient flow structure, with the dissipation of the energy, this simplified closure seems to be the only one that really gives you the right sign in the entropy dissipation, or it's the only case where we can write the entropy dissipation in some, it's really negative, so we kind of preserve this dissipation also in the macroscopic model. In general, I don't go into these details, but just, okay, for example, for the Kirchhoff closure, there's no reason that these things become, the entropy dissipates the right way. Okay, so as a final remark now, how would the patterns look like? So if we look for consensus, we look for a solution concentrated in the state. It's not really important how the weight distribution is. If we look for echo chambers or polarization like this, then the single particle distribution is concentrated in 2 or more states. But the interesting thing is, in the 2 particle distribution, we see that the weight should be 0 if the states are different. So we kind of find some concentration in weight, which we should infer from these models. And I just go back now to this very minimal model, with the binary states. So then we can come up with an equation basically for 6 variables. So it's the probability to have like same state and be connected, same state and be unconnected, or have different states and be connected or unconnected. Okay, these are the 6 cases. So we have like F++, same state and connected, G++, same state and unconnected, and so on. And you can, with this closure, just write a system of 6 ODEs with these appropriate weights depending on the rates depending on the relative states. And the crucial thing now is to look at the kind of 5th equation. If you look for the question of this polarization, so the question will be, will F plus minus go to 0? So this means that you are always unconnected if you have opposite opinion. And maybe I don't go into the details, but in these specific models, you can really prove that, in particular, that either you have a finite time where things get 0, or you go really to an infinite time. And in particular, if you go to if you don't have a blow up of something, which you don't really expect, then you can really show that this F plus minus goes to 0 as time goes to infinity. Okay. So this is just a very minimal first result. I think it's one of the open issues to get really a decent mathematical analysis of this kind of phenomena and patterns. And of course, also to have some mathematical analysis of this kind of higher order closures, and maybe even get some other reduced equations. And 2 points that I didn't mention here is, so far there was no interactions in the weights. There is something which is called social balance theory, which says things like, of course, if you're connected to someone, then it's more likely for the others to be connected. So then you have also some kind of interaction in the weights, which makes life even more complicated. And since a lot of people here are interested in control, I think one thing that would be interesting is to do some kind of control on the weights not in the sense that you control people's opinion, but maybe that you can actively suggest new edges or suggest people to link to others in order to avoid this kind of polarization of the society, which I think is a very useful goal in the end. Okay, I think I'm already over time. Thanks a lot for the attention. Here is a
Thank you very much, Professor Burger. Now, a very interesting talk, and we can have 5 minutes for discussing and questions. Do you have any questions or comments and anything? Do you have?
Masahiro, can I ask?
Sure, please.
Hello.
Go ahead. Please go ahead.
Can I ask, or Enrique, do you have some question or no?
No, please go ahead.
Okay.
I can ask later. Please go
First
ahead.
First of all, thank you, Martin. Sorry, I can. So, thank you for the. So I'm not expert on Zoom technology. It's clear. So thank you for your nice talk. Very interesting. So maybe I missed something. So you deal with bounded confidence, but which assumption you take on the communication rates that we call, if I remember, WIJ.
Yeah, so basically the idea is to reduce
at the beginning of your talk.
Yeah, so I mean, basically from the original model structure, it could be quite arbitrary. So the point is to have some kind of evolution equation, or could also be some stochastic processes which changes the WIJ. So that's the main difference, maybe to really bound the confidence. In bounded confidence, you say given the states, I compute the WIJ, but I think typically in this kind of dynamics, the timescales are not such that the weights are faster adapted than the opinions, for example. So you would have like something that maybe you have a higher rate to connect to someone who has a similar opinion, but it's not automatic. Yeah, that you have really this bounded confidence. But of course, in the cases where I should get consensus, of course, this, the kernels K and eta here should have the right properties. So K should have similar properties as you always have in these models. And also the eta should, have there is no support.
And you can include some leadership in your...
Yeah, that's another question, how you include leadership. If you would say this could be, for example, in these dynamics, if you have some kind of particles that maybe are leaders and do not follow us, so it's kind of maybe the asymmetry in the interaction that might be the leadership. So then you would have maybe I would put two different functions here, so that you maybe between leaders and non-leaders, there's a different kind of interaction and strengths to connect or to not connect, so that you have more people kind of following leaders than leaders following the others.
Okay.
Christina, okay?
Okay, thank you, Martin.
Do you have any maybe short questions or comments? Maybe shorter. Oh, yeah, please.
Yes, so I hear very badly. I don't know whether it's my connection or is the signal. The others are receiving the.
I can hear you. I can hear you well.
Yeah, we hear you well.
Okay, so so Martin, I'm sorry I could not follow all the details because I was disturbed by something else. But so what do you think of these mean field approaches? So here, after all, you start from some kind of discrete, say, particle paradigm. Then often people look to mean field games, but eventually you get to complicated even non-local PDEs, and then you have to make them discrete again. So how do you see the role of mean fields plus numerics on this? Is a way for you of reducing the complexity of the model, even though probably in the end you have to still deal with a discrete model?
Well, there are three answers. I mean, one is analysis. Okay, one motivation is if you can prove that things converge to something under, no matter how you do the simulation, is of course a big plus. If you cannot, then the question is, there are different microscopic models that lead to the same macroscopic PDEs in a sense. And then you could say, okay, I choose the one which are more efficient in simulation. And so, for example, if you come up with some discrete kind of flipping states on a lattice, this is usually very slow to simulate. If you can come up with some kind of ODE that describes the same for different particle systems, it is much more efficient to do. And the third question is kind of a discretization question. If you have some kind of knowledge of the limit and maybe ideally some quantitative estimates, you can be sure that, okay, for a certain number of agents, you already capture the main dynamics and you don't have to go to millions or billions of agents to get the right results.
Thank you, Martin. Thank you.
Okay. Yeah, Professor Burger, very shortly, I'd like to ask you a question for my curiosity, because I have been working also a bit similar problem, but namely internet network problem by the request of some company. My question is that also your method can aim at something like a framing of Twitters or internet boards for controlling.
Like you want to detect the bots or you want to put them?
Twitter sometimes is under framing. Then some companies very afraid of framing. Too many twittering against. Then some control for the transportation of the information or twittering by others. That is to some companies in Japan, not only in Japan, very serious interest. Then my question is that do you think even your method can be related or can give nice solution?
Good question.
Then you can get a lot of money.
Okay, I didn't think about that. Maybe yes, but it's a bit speculative what I say. But
okay.
But it's first, it would be one way to interact is to put some bot. Yeah, I mean, it's all for me. It's from an ethical point of view. Some of these things are quite delicate.
Of course, very
mathematical.
Very delicate. Of course, this is like a propaganda or propaganda.
Yeah, so I have to be a bit careful.
But I believe implicitly many companies are minding very much. Anyway.
Yeah, that's right.
Okay, then do you have any other short questions or comments? If not, we would like to thank the speaker, Professor Burger, for the excellent talk. Thank you very much, Professor Burger.
Thanks.
Okay, now we'd like to proceed to the next presentation. Say a bit behind the scheduling, namely plus 4 minutes or 5 minutes. Yeah, sorry for that shifting, say by 5 minutes. Then Eric, are you ready? Okay, very good, excellent.
Ready, so.
Okay, are you ready to start?
Is it fine?
Fine, I think so. Okay, now it's my great pleasure to introduce the second speaker, Professor Eric Sokolsky from Exmouth University. And he's not only an active researcher for inverse problems and especially related to the scattering theory, but also he's a very effective organizer for several conferences, organizing research team activities, and also promoting the younger. And I highly appreciate And today he will give a talk entitled by Borg-Levinson inverse spectral problems. The title was changed.
Yeah, title was changed.
So
Yeah.
could you please just start?
Okay. Thank you. So thank you, Masahiro, for the introduction. And I want to thank Enrique and Giuseppe for their kind invitation as well. Yeah, so I decided at the very last minute to change the topic of the talk. I mean, not directly the topic, but say I have decided to opt for a presentation which is say, less technical than the one I had previously chosen. And I think that this presentation is probably better suited to a 35 minutes talk. So at least I hope this is the case. So this talk is on Borg-Levinson inverse problems. And it is based on joint work with Mourad-Chouli, Otaret-Kavian, and Yavarkian. So here I want to essentially to discuss the following question. So it's an inverse problem. So we consider Dirichlet Laplacian in a bounded domain of Rd. So D is a dimension. It can be any dimension, so greater or equal to 1. And we want to know whether knowledge of spectral data of the Dirichlet Laplacian means, or at least determines the potential, the electric potential of the Dirichlet Laplacian. And as always in inverse problems, you know that we are interested in two types of results. So the first type of result, which is called uniqueness result, is an injectivity result. And when this result is true, one may investigate the second type of result, which is a stability result, which amounts to saying that the unknown coefficient, so Q here, depends continuously on the data. And so the outline of my talk is as follows. So I will just start by reviewing the main results in the one-dimensional case. And so these results are, of course, the Borg-Levinson results, and maybe one result which say paved the way to multidimensional result, which is the Gelfand and Levitan result. And then after that, I will jump to multidimensional results, starting from Novikov and so Novikov result, and then moving to the last multidimensional results that have been proved recently, which are asymptotic Borg-Levinson results. And so the techniques of proof used to prove the one-dimensional results is highly one-dimensional. So it's really based on one-dimensional techniques. For the two-dimensional results, the technique is a bit different, and I will try to explain a little bit the two main steps of the proofs in the third and fourth part of my talk. So essentially, the strategy in the proof of this result is to first to relate the Neumann data, so essentially the Dirichlet to Neumann operator, to the spectral data. And this is what, so I will show how we can do that in the third part. This is quite easy to do. And the second step generally is to relate the unknown coefficient, so the potential, to the Dirichlet to Neumann map. And this is made generally through the so-called Isozaki's formula. And so I will try to explain the fourth part, how we can do that. And once I've done that, I will just try to give an extensive bibliography on the results in inverse spectral theory, and more specifically, of course, here on Borg-Levinson inverse spectral theory. So let's start with the one-dimensional case. So here I will assume that omega is the interval 0, 1. And so there is a natural question that was asked initially and historically by cosmologists, which is to know whether the electric potential of this Sturm-Liouville operator here is uniquely determined by the spectrum of the operator, which is made here of eigenvalues, of course. And as you probably know, the answer is negative. And to see this, we can consider this unitary transform capital U, which symmetrizes any L2 function on 0, 1 around the midpoint of the interval 0, 1. And of course, this is a unitary transform, as I said before. And if we conjugate the operator AQ by this transform, we can show that we end up with the exact same type of operator, but now for the symmetrized potential UQ. So since these two operators are unitary equivalent, they are isospectral. And this is the case despite of the fact that I didn't assume that Q is symmetric about 1/2. So this shows that it is completely hopeless to try to recover the potential by the spectrum only. So additional spectral knowledge is needed actually to determine Q. And so this is the starting point of the work of Borg and Levinson. So they studied actually, they consider the eigenvalue equation of this Jericho Laplacian. And you see that they actually impose that the eigenvalue, the derivative of the eigenvalue as a fixed is equal to 1 at 0. But they don't impose, of course, that the eigenvalue is normalized. And what Borg and Levinson noticed is that if we consider, in addition to the eigenvalue, if we consider the L2 norm of the eigenfunction, then this spectral information is enough to identify the potential. There is a quite similar result, which is due to Gelfand and Levitan, which states the exact same thing, but now instead of using this normalization constant, they decided to use the normal derivative, the derivative at the endpoint of the eigenfunction. So this result is closer to saying the spirit of the multidimensional results that I will introduce further. So I will more or less come back to that later, but I just want to state that this result is more general than it seems, in the sense that we can just apply this type of result to solve inverse spectral result for, say, general Sturm-Liouville operators. So, for example, in the form of this operator A here, with conductivity C, you see there is a density rho and electric potential capital V. And the boundary spectral data for this operator are the exact same spectral data that were used in the theorem of Gelfand and Levitan. And what we show here is that knowledge of this boundary spectral data uniquely determines either of the three coefficients, C, rho, or V, when the two other coefficients are known. And this is true provided the conductivity and the density are sufficiently smooth. And this can be obtained from the Gelfand theorem by just considering the so-called Liouville transformation that is here, which is actually a coordinate transformation because C and rho are sufficiently smooth here. And it turns out that this transformation reduces the eigenvalue equation for the Sturm-Liouville operator to its normal form. So the normal form is here, and you see that the potential here, Q, is expressed in terms of C, capital V, and rho. And while in the same time, the boundary spectral data of the system are preserved, which means the boundary spectral data of the second equation, so the Dirichlet Laplacian here is the same as the boundary spectral data of the Sturm-Liouville operator. So by just applying the Gelfand theorem, we get that Q is known. And since Q is known, we can recover either of the three coefficients C, capital V or rho when the two others are known. So this is the idea of this method here. Okay, so I will jump now to multi-dimensional results. So in the dimension 2 or greater than 2. So the framework is the following. So we consider a bounded domain of RD, whose boundary is C2, and as before, bounded potential, which is real valued. And so we consider the self-agentization of the Dirichlet Laplacian in L2 of omega. So the domain here is H2, is made of H2 functions, which are in each on 0 as well. And as before, since the injection of H2 into L2 omega is compact, the spectrum is discrete, so it is made of eigenvalues, which are denoted by lambda n as before. And we consider an orthonormal basis, so orthonormal in L2 of omega, of eigenfunctions of AQ, which are denoted by phi n. And we define the boundary spectral data of AQ, or simply Q, as the sequence of all the eigenpairs made by the eigenvalues and the normal derivative of the eigenfunctions. So the eigenfunctions are in H2, so this normal derivative is well defined. So I call psi n in the following this normal derivative. And so the results, the similar results on this problem are the one by Narman, Sylvester Ullmann, and by Novikov, who prove independently that knowledge of this boundary spectral data, so all this data, uniquely determines the potential. So this is a uniqueness result. There is a stability result for this theorem as well, which was proved a bit later by Alessandrini. I will give the reference in the bibliography a bit later. But what I want to mention here is that to get this result, it is required that you know all the eigenpairs for all integers n. And Isozaki noticed a little bit later that actually the same result holds when finitely many eigenpairs remain unknown. So this is the so-called Borg-Levinson theorem with incomplete data. And you see that for this theorem to hold, we need to assume that a finite number of data is missing. So this number can be arbitrary, but it has to be finite. And of course, it is quite tempting to ask, or at least to investigate what happens when, say, capital N formally goes to infinity. And to ask this question, asking this question amounts to so is equivalent to asking whether there is an asymptotic Borg-Levinson theorem. And to my knowledge, the first asymptotic Borg-Levinson theorem was proved by Plemen Stefanov and Murat Shuli. So the answer to this question is positive. And I will state this result in its latest version, which was proved in the exact framework that is in a bounded domain here. That's the one that that is examined in this talk, because there is another result which was proved by Otaret-Kavian and Yavarkian and myself, with the same type of result, but in an unbounded domain with boundary periodic conditions. So I prefer to state this result in this framework here. And so the result is as following. So we assume that we know the asymptotic of the boundary spectral data. So this means essentially that the limit, we assume that the limit of the difference of the eigenvalues is 0. And we assume a summability condition on the normal derivative of the eigenfunction, or more precisely on the difference of the normal derivative of the eigenfunctions. So this summability condition is denoted by capital S here. And under these two conditions, so you see that the second condition, of course, is stronger than just requiring that the limit of C1n and the one of C2n coincide in L2 of the boundary. But nevertheless, you can see that this condition is satisfied, of course, by the data of the incomplete, of Isozaki's incomplete Born-Levinson theorem. Well, in this case, we get the uniqueness result. And it turns out that there is a stability result as well. But for that, we need to assume a bit more. So here we assume only that Q is bounded, real valued and bounded. But if we assume that Q is H1, in addition to be bounded, so H1, and if we assume that Q is known on the boundary of the domain, we get that Q can be further stably recovered by, say, the limit of the eigenvalues. And you see that for this result to hold, it is required, of course, that the summability conditions S is satisfied. But the nice thing here in this stability inequality is that there is no quantitative information on the partial derivative of the eigenfunction needed in the right-hand side of the inequality. Okay, so this is essentially I think the last version, I mean, of the asymptotic Born-Levinson theorem, and I will turn now to explaining how these type of results are obtained. So not necessarily for the asymptotic version, but just say for the initial version of the theorem with the full data. So I will just try to explain first how we pass from spectral data to Neumann data. And to do that, we consider the Gelfand problem, which is made of this eigenvalue equation and this Dirichlet boundary condition. So here the boundary condition is sufficiently smooth, so there is an H2 solution, because here the energy, so the spectral parameter lambda, is taken in the resolvent set of the Laplacian. Okay, so we know that there is an H2 solution. I will not explain that. And it turns out that this H2 solution can be expressed in terms of the boundary spectral data. You see psi n lambda n here, but here it's not exactly what we expect because we have the eigenfunction. But it is very tempting to try to generalize this type of formula for the normal derivative of the solution, u lambda, here. And so in this case, to replace phi n by psi n. So this is more or less the type of result that we are looking for. So first, for this representation of the solution, so this is something that is well known. So essentially, we decompose the solution on the orthonormal basis of the eigenfunction, and we just show that each coefficient here has the right expression, which is here. And to do that, we only multiply the eigenvalue equation by phi n, and we integrate by part. Take into account that phi n is 0 on the boundary, that u lambda is f, and that aq phi n is lambda n phi n. So once we do that, we get the expected result. So we have this representation of the solution. And as I said before, what we expect essentially is that we have the same type of representation if we differentiate this equation with respect to the space variables, and it turns out that this is not true, because this series is converging only in L2 and say not in say in H2. And nevertheless, if we use two different energies, so lambda and nu, so two different spectral parameters, lambda and nu, which are taken in the resolvent set of the operator AQ, it turns out that the expected formula holds for the difference. I mean that for the difference of these two functions, so for the normal derivative of the difference of these two functions, we have an expression which is given only in terms of the boundary spectral data. So the eigenvalues and the functions phi n here and here. And so the proof here is actually quite easy, because we just express the solution u lambda minus u mu by linearizing the system. And so we see that, as before, this solution, so which I call V here, so it is solution to this system now. It is expressed by this resolvent applied to u mu. We use the spectral theorem, so we get this expression for V. And obviously, the first term here was computed previously in the proof of lemma 1. So we get that this scalar product is equal to this quantity. So we plug this quantity into this one, and we get this representation of the solution V here. And now it is only to prove that V, that this representation, this series converges in H2, which is easy to see, as we know that V is in the domain of AQ, and we know that AQV, by the definition of V itself, is given by this expression. So now we just replace by the preceding expression, and we get that this convergence of this series in the domain of AQ. And the conclusion is obtained by just the continuity of the, say, the trace from H2 into, say, L2 or H1.5, and the equivalence of the norm of the domain of the operator AQ and the one in H2. So we get our result in this way. So you see that we can actually pass from, make the connection between the spectral data and the normal derivative, say, of the solution to the previous system, which is actually the Dirichlet-Neumann operator applied to F, by just using the information on the spectral data. Okay, so once we have made that, the second step is now to connect or to relate this information to the potential itself. So what we are aiming for here is to, so we consider, so this same problem as before for an eigenvalue, so sorry, a spectral parameter lambda tau, which is given by this expression. And you see that the imaginary part of lambda tau is equal to 2 times tau. So tau is a large parameter, large real parameter. So this quantity goes to infinity as tau goes to infinity. And so we define the Dirichlet-Neumann operator of this operator as follows, so in the usual way. And our goal here is to relate, so the difference of the two potential Q1 and Q2 to the asymptotic behavior as tau goes to infinity of the difference of these two operators S1 and S2, where S1 and S2 is just the scalar product in L2 of the boundary of the Dirichlet-Neumann operator applied on a test function F2 plus, so scalar product with another test function F2 minus that I will define in the next slide. And so once we have done that, we will show that we get this connection, which is called the Isozaki formula. So the test function are built in the following way. So the idea is to build two functions which satisfies the three conditions that are expressed here. So first we want this this function to satisfy the Laplace equation with energy lambda tau plus or minus here, and we want that the Hermitian product of these two functions converges to, say, this planar wave as tau goes to infinity, where xi here is simply an arbitrary fixed vector of Rd. So this is essentially what we expect, and we expect on top of that that this function is uniformly bounded uniformly in tau, in omega. And to build this function, so clearly from the first equation, we see that we can take f tau in the form of this exponential function, where n tau here is a unitary vector. So this is the Euclidean norm. So this denotes the Euclidean norm of n tau. So we need a unitary vector, and if n tau is unitary, you see that clearly this expression satisfies the first condition. Now we want the second condition to be satisfied as well. And to do that, well, we will design n tau by the superposition of two vectors. So one vector, which is collinear to the direction xi, and another vector, which is collinear to a unitary vector eta, which is orthogonal to xi. So the prefactor of xi here is just given by this condition. So by just using this second condition on the Hermitian product of f tau plus f and f tau minus, we can see that the right prefactor to choose here is 1/2 tau. And so since we want a unitary vector, this determines the parameter beta tau as this one here. And then we check that the third condition is satisfied. Okay, once we have done that, I think I have only 1 or 2 minutes left. The idea is just to see that if we probe the system with f tau plus, the solution to the system behaves in the same way as f tau plus in L2 omega as tau goes to infinity. So the idea is just to use a so we lift up f tau plus by the function f tau plus itself here. So we linearize the system, and so we see that the solution v, which is a difference of u and f tau plus, is given by this expression. So this is a resolvent. It is well defined, as we noticed that lambda is a resolvent set of AQ. And since the imaginary part of lambda tau is 2 times tau, so the distance of lambda tau to the spectrum of AQ is at least 2 times tau. So we can actually bound the L2 norm of the resolvent by 1/2 tau. So this gives us that Vj scales at most like 1/tau. So we see that this quantity goes to tau, goes to 0 as tau goes to infinity. Okay, and now, okay, I've almost finished with that. So the idea is to prove that the Fourier transform of the difference of Q1 and Q2 is just the limit of S tau, where I remind you that S tau is just obtained as the scalar product of the difference of this normal derivative of these two solutions with f tau minus, okay? And to do that, the idea is just to multiply, so the eigenvalue equation here by f tau minus, and to integrate by parts. So we get 3 terms. So for the first term, this one, we use the fact that f tau minus is solution to the Laplace equation minus delta minus lambda tau minus f tau minus equal to 0. So this guy and this guy disappear, so we get that. The second term, okay, we just keep it as it is because it does not depend on j. And for the third term, this is simply fj tau. So we get the expression of sj tau as the sum of these two first terms here, okay? So Sj is explained in this way. If we make the difference, you see that this term cancel out and we get only this expression. well, once we have done that, we remind that uj is equal to f tau plus a correction term that goes to 0 as tau goes to infinity. So if we use this expression in this one, so we get that s tau minus this quantity is equal to this one. And thanks to the previous result, this remaining part here, so this one, we see that it scales like at most like 1 over tau. Now, once we have done that, we remind that this Hermitian product goes to exponential minus xi x as tau goes to infinity. And by just using the dominated convergence theorem, we get the expected result. Okay, so this is how we can actually relate the difference here of the so the Fourier transform of the difference of the two potential to the Dirichlet-Neumann map, which itself was linked or related to the spectral data. Do we have 2 minutes just for the bibliography, or I'm already over time?
No, you can have still 1 or 2 minutes.
Okay, so I just want to give, okay, I'll start with the classical papers that I have mentioned already. So the paper by Nachman, Sylvester Ullmann, and by Novikov, and the stability result by Alessandrini, which I mentioned in my talk here. And another result, so there are results where we can, so we try to reduce, say, the number of data. So there is one way to do that, which I have not presented in this talk. So one way is just to use a partial Neumann data. That means we want to measure the normal derivative of the eigenfunction of the subboundary on a subboundary only, and not on the entire boundary. And this one made in this paper. But for the incomplete Bohr-Levinson theorem, so there is a paper by Isozaki, which is here. And as I said before, if we go to the asymptotic Bohr-Levinson theorem, so the 3 results that I wanted to mention are the following ones. So the first result, as I said, by Plemen Stefanov and Murad Shuli, and the 2 other results that I have mentioned before. So this one is in the framework of the periodic waveguide, and this one coincides with the framework that we are examining in this talk, that is for a bounded domain. In this talk, I'll discuss only the case of bounded potential, but we can try to adapt this theorem to the case of unbounded potentials. So I mentioned 2 papers in this direction. The first one is for potential in the LP class, where P is strictly greater or greater than the dimension over 2. So this is a paper by Peivarinta and Serov. And in the case where P is equal to D over 2, there is a recent paper by Porola, which is mentioned here. And to finish my talk, I would just like to give and to mention 2 nice applications of inverse spectral problems. So the first result is due to Canuto and Cavian. And they noticed that we can solve a parabolic inverse problem by using the Borg-Levinson theorem. Just what they showed is that actually knowledge of the Dirichlet-Neumann map at one fixed time, uniquely determines the boundary spectral data. And since you know the boundary spectral data, then by the Borg-Levinson theorem, you can determine the potential uniquely. And this is what they made here. So they prove that we can uniquely determine the potential by knowledge of the Dirichlet-Neumann map, parabolic Dirichlet-Neumann map at one arbitrary time. And the same result was extended to the case of time fractional diffusion equations. So in the subdiffusive and super diffusive case, so in this paper. And I think I have finish my talk. So I thank you for your attention.
Thank you very much. Very excellent talk. And now we can have 3 or 4 minutes for discussing and questioning. Do you have any comments or questions? Yeah, Eric, may I ask, I'd like to make information about your results, 2020, the asymptotic Levinson equation. I am not particularly sure, but definitely your results is improvement of the uniqueness by Churi and Stefan, because they proved the uniqueness under some asymptotic something like a ratio of eigenvalues or something.
Sorry, Masahiro, because I can't hear you very well. No.
That result, yes. The first condition and the second condition.
Yeah.
More generous than the condition in the paper by Churi and Stefano.
Okay.
Namely, as like a corollary in their paper, they prove the uniqueness. I think lambda 1n minus lambda 2n is under some asymptotics.
Exactly.
And also something like eigen boundary trace of eigenfunctions is subjected to some asymptotics. I forgot the exponents, but here your result does not specify the ratio. Yeah, that's why I would like to confirm that this result is an improvement for such uniqueness results in by Churi and Stefano. Am I correct?
Yeah. So if I understand well your question, yeah. So you're asking whether this summability condition actually is satisfied by the data. So by the function who satisfies the condition of Stefanov theorem. And yeah, actually there is one more condition, if I remember well, in their paper, and it is that I think the potential even for the uniqueness result, if I'm correct, they assume that it is H1 on the top of that.
Okay, awesome.
And yeah, of course, so they assume that the difference of the eigenvalues is bounded by n to the power. I can't remember exactly how much. Impose decay. So this is stronger, and yeah, and there is a similar condition, if I remember well, for the eigenfunctions for the eigenfunction, and in this case, yeah, I think that it satisfies our summability condition, if I'm correct.
Yeah. Therefore, I believe that your result is an improvement result in their paper.
Sorry, I can't hear you now. Sorry.
It's okay. No.
I'm sorry, I don't know why, but the connection.
Yeah. I like you to make advertisement for your own result.
Thank you.
But it's okay.
Thank you.
No, thank you. And do you have any other questions? I occupied the time so much. Do you have any other questions? It is okay if you have.
I have a question, please.
Please go ahead.
Thank you very much. Thank you very much for your presentation. It's interesting. I have a question about this uniqueness result. I don't know if is it possible to show this uniqueness result by considering.
Excuse me, there are too many open microphones.
What? I'm sorry.
I think that there is some noise from. But now the situation is okay. There was a background noise, but
now it's good.
Yes, please. Can you repeat your question, please? Because.
Okay. Thank you very much. My question is, I don't know if is it possible to have this result with observation just on a part of the boundary, not the whole boundary?
Yes, I mean, I'm not talking about the asymptotic result, but I'm pretty sure that you can adapt to the asymptotic result as well. But as I mentioned in the bibliography, there is a paper by Maseiro, and so where is it? It is here. Maybe I went too fast. No, here. This result by Mourad Belaswed, Mourad Chouli, and Maseiro here. So you get you get a uniqueness result and a stability result by local Norman data for the potential. But if I remember well, it is a log stability result. But you get this type of result. You can find it in this paper here. And here they consider, so they measure, so they observe the normal derivative of the eigenfunction of the subboundary of the boundary only.
Okay, thank you very much. Thank you.
I don't know, but I can't hear you, Maseiro, so I'm sorry if. I think that we can't hear you at all. I mean.
Maybe the microphone of Professor Yamamoto is mute.
Mute. Sorry. Oh, sorry. Then, unfortunately, now the time is over, and the previous question is very interesting and important. Therefore, if I forgot the name, if the person asking a question is interested more in information, please send me your email address. Then I will send some information. Is it okay? I forgot the name.
Okay.
Yeah. By chat, you can your email address. Okay.
Okay. Thank you very much.
Okay. Now the time is over. Then sorry, a bit longer than the scheduled timing, but I'd like to close this session. Now I think 7 minutes behind the scheduling. Then how to take the cafe break? Giuseppe, could you please make an announcement, please?
No, now there is the lunch. Then we start.
Sorry, lunch.
Okay, maybe different. The lunch.
Maseiro is jet lag.
Time only.
Jet lag, Maseiro, no?
Yeah, jet lag. Sorry.
No, but we start again at 3 p.m. With the Professor Oleg Imanovilov, and the chairman will be always Professor Maseiro Yamamoto. See you later. Good lunch or good break.
Thank you very much. Yeah, thank you. I wish you buon appetito and nice lunch. And see you later. Bye.
See you later.
Ciao.
Bye.
Thank you, Eric. Sorry, sometimes the voice connection is not so good. Yeah.
Now it's good, but when you asked your question, actually, it was actually not good. I don't know why, but because almost at any other time it was fine, but just when you asked the question, I had troubles hearing you. But
maybe somebody wants to sabotage.
Yeah, it happens sometimes. Okay. Okay, maybe I will send you an email because we need to decide when we meet next time for the organization of the meeting.
Yeah, sure. Yeah.
Okay.
Okay,
so
then.
Have a nice lunch. Have a good lunch. Bye-bye.
Already I have finished the dinner.
And thank you again. Bye-bye.
Welcome. You're very welcome. I highly appreciate your talk because very original talk, not only, but also like a survey-like talk.
Yeah, this is what I tried to do because...
that is not so simple because the inverse eigenvalue problem has a long history.
Yeah, but actually it's good to do that because even it's good sometimes to do that because you realize that there are many things that you actually don't know, even topics that you worked on quite intensively. So sometimes it's good to do that, and I think it's a good advertisement for this type of problems. So
Sure. Yeah, so many interesting problems.
I hope so. Anyway. Okay.
Well, okay.
So
See you later.
Have a nice lunch. See you later. Bye-bye.
Later, bye.
Bye-bye.
Giuseppe, ciao. See you later.
Thank you very much. I'm sorry for your time.
Buon appetito.
Grazie. Thank you.